Here we discuss about a project. A 57.2 nanowatt, 1.3 to 5 volt VN, minus 85 decibels PSRR, 50 microsecond startup time, bandgap reference circuit. Here, the bandgap is priority 1. A bandgap reference circuit is a fundamental analog block used to generate a stable reference voltage that remains nearly constant across changes in temperature, supply voltage, and process variations. Recent advances in bandgap reference design focus strongly on ultra-low power operation, fast startup, and high power supply noise immunity to meet the needs of modern IoT and intermittently powered systems. In this paper, the bandgap reference circuits are essential building blocks in low-power sensors, biomedical devices, IoT nodes, and mixed-signal systems on chip, as they provide a stable and temperature-independent reference voltage for ADCs, voltage regulators, and bias networks. However, when conventional bandgap reference designs are scaled to deep submicron technologies, such as 45 nanometer CMOS, their performance degrades significantly due to increased leakage currents, reduced analog gain, poor power supply rejection, and slow startup behavior. In this work, the bandgap reference is redesigned to address these challenges while preserving the fundamental PTAT and CTAT voltage generation principle. The core bandgap still relies on the combination of proportional to absolute temperature and complementary to absolute temperature components to achieve temperature compensation. The key improvements are introduced in the regulation and startup architecture. A pre-regulated amplifier is used to isolate the reference voltage from supply fluctuations. By regulating the internal bias node rather than directly relying on the supply, the circuit significantly suppresses supply-coupled noise, leading to improved power supply rejection ratio. This is particularly important in 45 nanometer CMOS, where supply noise and substrate coupling are more pronounced. To ensure fast and reliable startup, the design introduces an RC-filtered pre-bias startup network. During power-up, this network gently pre-charges critical internal nodes close to their nominal operating points before the main bias loop becomes fully active. The RC filter smooths the injected startup pulse, reduces sudden current surges, and prevents voltage overshoot or undershoot at the reference node. As a result, the bandgap avoids metastable states and reaches steady operation quickly and reliably. By combining pre-biasing with controlled regulation, the proposed system achieves a stable reference voltage during the settling phase, improved noise immunity, and faster startup compared to classical bandgap references. Tanner EDA simulation results confirm correct temperature behavior, enhanced PSRR, robust startup performance, and low quiescent power consumption, demonstrating that the proposed bandgap reference is well suited for modern low-power and deeply scaled integrated systems. Now we can verify the paper circuit designs. Figure 1 shows the circuit of low-power bandgap reference that generates a stable, temperature-independent voltage using a P-TAP-C-TAT core. A pre-biased pulse current injection startup circuit ensures fast and reliable settling, while a pre-regulated amplifier improves power supply noise rejection. The BGOK block verifies both voltage and current stability before signaling that the reference is ready for system use. Figure 2 shows in this paper implements a low-power bandgap reference where the PTAT-CTAT core generates a temperature-stable Vref. A pre-regulated amplifier isolates the core from supply noise and improves PSRR, while the bias and current mirrors ensure accurate low-current operation. The IOK detector monitors internal currents to confirm stable operation before the reference is used. Figure 6 presents the complete startup and readiness detection architecture of the proposed bandgap reference. The design combines pre-biasing, controlled pulse current injection, and dual condition validation, voltage and current, to guarantee fast, stable, and reliable startup under ultra-low power operation. The architecture is divided into 4 functional parts: the pre-bias circuit, current injection circuit, startup timing behavior, and BGOK generation logic, with a comparison to a traditional P-startup. This work we design in Tanner EDA at 45 nanometer CMOS technology. We design all the circuit separately with proper test bench. This is the BGOK circuit and simulation. This output working as an AND gate model. This is a circuit of BGR and its simulation results. This is circuit design of IOK and its simulation results. This is the proposed architecture circuit. Here, it's have startup circuit, BGR, VOK, IOK, and BGOK. To improve the startup circuit along with the implementation of the RC filter in order to reduce noise and improve the reference voltage in the final design. The final output of bandgap reference circuit showing with temperature sweep from -40 degrees to 125 degrees testing. And finally, we analysis the performance evaluation of this work and prepare a comparison table. And we written an abstract document for this work with title, base paper abstract, improvement, proposed title, proposed abstract, general notes, existing system, disadvantages, proposed system, advantages, related notes. Finally, literature survey and reference. Thank you.
Are you planning to publish your next innovative research in IEEE Transactions on VLSI 2025? Welcome to NXFE Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At NXFE, we provide novelty-based VLSI projects carefully aligned with IEEE Transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation-recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE Transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join NXFE Innovation, shaping your future for VLSI research.